Welcome to Lecture 10b, entitled Double Integrals over General Regions. In this particular lecture, we're going to be discussing some additional techniques for solving double integrals over general regions. The material that's being covered comes from section 16.2 of the text, and the objectives are to develop tools for computing double integrals in a Cartesian coordinate system with integration limits on the inner integral containing functions. The concepts and visualization skills that we'll be discussing here include determining the volume between bounding surfaces and also a decomposition method, which essentially allows you a technique for dealing with complex regions where you cannot do the integration in one step. As usual, the second slide basically just covers a summary of the slides to follow. So as usual, we'll skip over this slide and move on to the next one. All right, so now we have a slightly different problem. Here we have two surfaces, an upper surface and a lower surface. And we're interested in computing the volume between those two surfaces over a region, where the region is more or less the shadow that's cast by the two surfaces onto the XY plane, which is the region labeled in green. So we need the height between the top surface and the bottom surface integrated over the region to compute the volume between the two surfaces. Hence you'll see here the integrand is just the difference between F and G, which are the two surfaces. So that's this vertical height as a function of an X and Y. And then we integrate that over the region to compute the volume. Again, one of the conditions is that this be greater than or equal to G, otherwise it has no physical meaning. All right, so let's take an example. This is the volume between bounding surfaces. The problem asks you to find the volume of the solid bounded by the parabolic cylinder, z equals 1 plus x squared, and the plane z equals 5 minus y and y equals 0. So if we look at it from a picture point of view, this is the first thing we need to do is to sketch it. Parabolic cylinder, when you hear the word cylinder, it means one of the coordinate variables can be anything. So if you look here, z equals 1 plus x squared, what does that mean? That means y can be an element of R. And so this section that you see here, this blue, which actually comes around the back side, this extends in the y direction to positive infinity and minus infinity. And we're just going to show this section basically bounded. The plane z equals 5 minus y, which is this one, and y equals 0, which is basically just this back surface that's shown in shadow. So y equals 0 would be just the xz plane. So we got the xz plane, and we have basically this surface here. So if we were to look at this now in terms of the problem where we're dealing with what is the upper surface and what's the lower surface? Well, the upper surface basically is this surface that you would see here, which is z equals 5 minus y. And the lower surface basically would be this parabolic cylinder, which is 1 plus x squared. Notice that this is larger than this, and that this is a point at which the intersection takes place, and of course we'll need to know that. Okay, so this basically allows us to draw this, and so now we need to determine the region, and the region is determined by the intersection contour between the lower and upper surfaces. So if we equate this value of z with this value of z, which is what I've done here, then we end up with an equation y equals 4 minus x squared, and this describes a curve on the xy plane. So that's the curve that you see here. This is actually the shadow of this object onto the xy plane, just by equating those two. Right, so that's one, but a region has to be closed. So the other line is defined by y equals 0, right? But y equals 0 basically, intersecting with the xy plane, basically would be the line that goes from x equals here to x here. And we need to first determine what this value of x is in this. And we do that by basically equating y equals 0 with the parabola y equals 4 minus x squared. And so this gives you a solution of x equals plus or minus 2. This will be the lower bound on x. This is the upper bound on x. So we have now basically everything we need. For the region, we have an upper bound for y, which is this parabola, a lower bound, which is this line, like along here. And we have basically x going from -2 to +2. Okay, and so that would be a vertical line that goes this way, represent x equals -2, y can be anything, and x equals 2, and y being anything in this direction. So this is the way we like to usually set it up. The region limits on y. This you pick off as the upper limit. This you pick off as the lower limit. And limits on x. This is the lower bound on x. This is the upper bound on x. This will be the inner integral. This is going to be the outer integral. So this is more or less how things are established. All right, so let's carry on. So the height, which is in red, is just the difference between this surface and the blue surface. This minus this, which is 4 minus y minus x squared. All right, so now we look at this function here. We notice that if x is negative, it makes no difference. X squared still is the same. So integrating this function between minus x and 0 to positive x basically gives you the same result. It's symmetric. All right, so it's symmetric basically about the y-axis. So the contribution from x equals 0 to x equals 2 is the same as the contribution from x equals -2 to x equals 0. So that's one point to make note of. The second note is that the upper limit of integration for the inner integral, is the same for x equals 0 to x equals 2 as it is for x equals -2 to x equals 0. Therefore, if we can integrate x from 0 to 2, we can integrate from x from 0 to 2 and multiply the result by 2. I mean, that's just a method for simplifying the calculation. Of course, you can do the full integration if you wish. There's no difference. It's just an extra step, and which is fine. So again, the red lines basically represent z, which is the difference between the two surfaces. The blue line is the integration range for the outer bounds, which is from -2 to +2, and the gold line is the integration range for inner bounds between this line and y equals 0. So here we basically have done the calculations. So there's the height as a function of xy. So there's the bounds on y equals 0, y equals 4 minus x squared. And I've broken it up to two separate intervals, from -2 to 0 for x, and from 0 to 2 for the second part. I could have left this -2 to +2, which would be fine, nothing wrong with it. But as I mentioned earlier up here, that whether you put x equals -2 or +2 doesn't matter. This still remains the same. And so, in fact, what we can say is that this integral makes the same contribution as this integral, and therefore, if you take any one of these two, we'll take this one, multiply by 2, it's equivalent to the sum of these two. So that's basically what I've written here. So if you expand this out now, you can integrate it, and I'm not going to bother to go through it. This is just holding, basically, in this case, the first round, holding x as a constant, and then the function you're left with is just a function of x, and then you integrate with respect to x between the lower bound of 0 and 2. And the final result just is 256 over 15. All right, something else that sometimes comes up is to find the area in the xy plane using double integrals. Well, we know that if this here, basically f, has units of meters, then this is a volume. All right, so the integral of this is a volume. But let's say we keep this value as a constant value 1, but call it units of meters. Well, then the 1 can come outside. And so, in effect, what you're computing is an area. So whatever's left in here is just going to be an area. Times unit height 1 won't make any difference. And so this is a simple way. Sometimes it's just determining what the area of the region would be. This is just an interactive version of that. Okay, so the last thing I want to look at is something called the decomposition method. And so this type of problem comes up frequently if you're dealing with non-standard regions. And let me describe what I mean by that. So for instance, integration over a single region is not possible if at least one of the following conditions exist. Okay, 1, a given contour bound is defined over its range by two different functions, and the contour bound is continuously differentiable. So that's an example that can occur. And I'll look at some of the pictures below to sort of go through each one in turn. Secondly, the contour bounding the area is not continuously differentiable. Thirdly, the function describing a contour bound is not one-to-one. So I'll go through this in more detail in a moment. So what is the solution? The solution is to break the region into subregions if either one of these three conditions stated above exists. And so, for example, let's say you have region R1 and R2, and each has to be handled separately. Then you would integrate over region R1, which means this. You'd integrate over region 2, which is this. If you add these two together, then this would be equivalent to the total region. Now, you would not be able to do this in one go. You'd have to do this in 2 steps. All right, so then let's look at the examples I've given below, which are available if you just push on this URL here. I just briefly mentioned what these toggle switches are. Discontinuous basically is meaning discontinuous differentiability. And so this would be the example that you see here. If you follow the contour, right, for instance, if you have to integrate, you'd have to have an upper bound and a lower bound, and you have x equals at some on this side and some value of x on this side. But if you look at this line, it's continuously differentiable. X equals -3 and x equals +3, no issue, straight lines. But this, if you follow this curve, it's not continuously differentiable. We got a problem. So that means you have to break this region up. In this region, this is continuously differentiable. In this region, it's continuously differentiable. So this is piecewise continuously differentiable. So that means we'd have to call this region 1, for example. This would be region 2. So we'd have to integrate over this region, and then integrate over this region, and then sum the results together. All right, so what about another one? Multi-value or not one-to-one. So if you look at this particular example here, I'm calling this a multi-value problem. The reason being is that the way I constructed the functions, if you look at this contour here, okay, at this point here, the function changes. So the function for this region is not the same as the function for this region, but I designed the function such that if you were to look at the derivative, if you look at differentiability, you'd find that basically this is one continuous slope that goes the full distance. So there'd be no issues with this one. However, because these are two different functions, I'd have to break it up. So what would be the contours in this case? For one region, this would be one upper bound, this would be a lower bound. The lines would be here, that's for the x bounds, and here. For the other region, you'd have this as an upper bound for a line, this is a lower bound for a line. And for x, your bounds would be this line here and this line here. All right, so if you go to the simulation and click on one-to-one, the only difference will be that this whole object will be rotated by 90 degrees in a counterclockwise direction. The labeling will now be y here and x, y will be here and x will be here, or in the opposite direction, it doesn't really matter. But then the problem becomes one of, if you draw a straight line along here, you'll find that you get a contact point here and a contact point here, which means for a given value, right, of x or whatever you've chosen to be along this axis, you get two values for y. This is a case where we have multi-value. We do not have a one-to-one correspondence. So in that case, you would have to break it up into an additional region. So in this case, because this function is not the same as this function, and also going from here to here would be okay, and from here to be here, we'd end up having to break this into 3 regions if you look at this thing basically flipped in a counterclockwise direction. Anyway, I suggest that you click on one-to-one, and you can visualize what's going on. You end up with 3 regions in that case. Okay, so let's look at a simple example illustrating the decomposition method. So let's look at this now. We want to set up the integral for integration over the full region. But we know we're going to run into problems. Why? Because if you follow the upper contour, it's not continuously differentiable. So that means you're going to have to, in this region is continuous differentiable, and this region is continuous differentiable. That means this will have to be considered region 1, and this is region 2. The other thing is determine what are the bounds on x. Well, it'll be the intersection between this line and this line, which defines this intersection point, and this line, which defines this intersection point. So from that, you can determine what the upper bound on x would be. With these two different regions, you would have 0 to this value, which would be 3 for one region, for the x bounds, and for this one would be from -2 to 0. The upper bound for this one would be, for y, would be 4x plus 12, and for the lower bound, it would be the parabola here, which would be equal to y equals x squared. For this region, the upper bound for y would be y equals minus x plus 12, the same, and the lower bound in this case would be, again, y equals x squared. So that's basically what you see over here. Region 1, you got x squared lower bound, 4x plus 12 upper bound, okay, and lower bound would, the outer integral, lower bound is -2, upper bound is 0. So this basically would be the computation of the double integral over region R1. Similarly, for this region here, you're going from 0 to 3, and so that's what you see here. And the integral is with respect to y, which would be from this line, which is minus x plus 12, to the lower line, which is x squared. Again, just to reiterate, this has to be larger than this, and this has to be larger than this. I'm not going to do the integrals. You can do them yourselves. F is not given anyways. But if you want to look at the total integral over this region of this function here, you just take the sum of region 1 and the sum of region 2, and that's equivalent to the integral over the full region. So as usual, there is a interactive visualization of the previous problem. It's just a case we've seen in many cases where the textbook provides some additional information. So feel free to play with this. This basically just shows the process of integration when you're dealing with a region which needs to be broken down into subregions. So the last problem we'll look at is one from chapter 16.2, that is question 97. That's again double integrals with multi-regions. And you're given that R is a region between both branches of the function y equals 1 over x, and the lines y equals x plus 3 over halves and y equals x minus 3 halves. So the first part of the question asks you to sketch the region R, and so that's basically what I've done in the upper right. So if you look here, this line that you see here, this represents y equals x plus 3 halves. This line here represents x minus 3 halves. And these two curves represent the curve y equals 1 over x. This is for x less than 0, and this is for x greater than 0. Second step is to evaluate the integral over the region, that is the area, and determine the area of the region. Well, the first thing you would want to check here, given that the region is this here and here, you have to make sure that the bounds of the region are continuously differentiable. Now, the outer bounds are just basically lines, and so, for instance, an outer bound would be here, and an outer bound would be here, if you're looking at the region as a whole. But if you then look at the bounds on the function y, which would be, this is the upper bound, and this is the lower bound, this bound is not continuously differentiable. So we need to break it up into a number of regions. And so if you look at this very carefully, you'll find that at this point here, it's not differentiable. And so what we do is we draw a vertical line here, and at this point it's not differentiable. So we draw a vertical line here. If we look at this as a region, and this as a region, and this a region, then each of these three regions basically have boundaries which are continuously differentiable. So this would be an upper boundary for the inner integral. This would be the lower boundary for the inner integral. For this region B, this would be the boundary for the upper integral, the inner integral. This would be the lower boundary for the inner integral. And finally, for region C, this would be the upper boundary for the inner integral, and this would be the lower boundary for the inner integral. As far as the boundaries on x are concerned, which is the outer integral, it would be here, 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 and here for the specific regions. So it's not given as to what those boundaries are, but by looking on x. But if you look at this particular region, you'll notice that this point can be determined by basically equating the function for this line with 1 over x. This boundary point can be determined by equating this function 1 over x with the line x minus 3/2. This boundary can be determined by equating the function x plus 3/2 with 1 over x. And this can be determined, this boundary can be determined by equating the function 1 over x with x minus 3/2. Now, if you do that, you'll get all the points for x. So you'll have a boundary here and a boundary here for region A, a boundary here and a boundary here for region B, and a boundary here and a boundary here for region C. These would be the outer bounds, that is for x. So in doing so, then you can set up the integral for each region. So this is for region A, region B, and region C. If you add these up, basically you'll end up with this result. So just go through the physical process and you'll see you'll get an answer that's this. Next step would be to evaluate, for example, a function dA. And so the only difference now is the substitution of xy in here. The bounds do not change. It's just that this would represent some piece of information. And if the bounds on xy are such that xy is always greater than or equal to 0, then this would be just the volume of the region, where this would be the height. On the other hand, it might be a density of sorts, a mass density, so you'd be computing the total mass over this complex region. So that concludes Lecture 10b. Thank you for listening.